Dear friends and members of the KITION Planetarium Observatory, I would like to welcome you on behalf of our Science Center and our team to our online session, another online session, last Tuesday of every month, free online Science Café for everybody with guest speakers from all over the world. Tonight we have our own space scientist, Ekaterini Demetriou. She will talk about one of the latest, with some of the latest discoveries, and also one of the latest missions that reached to its. I'm talking about the telescope, James Webb Space Telescope. It reached its position and started sending us very valuable images. So, Katie, can you inform us?
Sure, of course. I'm going to share my screen.
Yes, please.
And then we'll begin. Thank you for inviting me to speak about this.
Great pleasure.
Okay, so it's been a very exciting July, very exciting, with announcements and lots of media and lots of press and Joe Biden. Very, very exciting. So I'm going to just tell you a bit of the story behind how James Webb Telescope got where it got, and a little about the rationale of the telescope itself and some details about the images. So on July the 12th, we had the first unveiling of these images, and it was right in everyone's face. I mean, you've got this doodle on Google. How many of you actually saw this? If you saw this, you could raise your hands, or like. So this was like, so practically, you know, millions of people must have seen this doodle when they went to search on Google. Now, I was in London, and there was a stunning sight. So this is Piccadilly Circus, and the first images from the web, the first color images were actually on the famous big screen on Piccadilly Circus. These aren't my pictures, by the way, so I'll put in the credits after the end whose they are. So it was absolutely stunning. It was also on Times Square, so another big screen with these pictures. So if you were on holiday, maybe you missed it, but I doubt it very much because it was everywhere. Now, the James Webb Telescope, the story begins in the 90s. This telescope is designed to measure radiation coming from objects in the infrared. So we see in the visible, the famous Hubble telescope, it detects radiation in the visible, and it does have some instruments that capture the infrared. But as soon as it was launched and the corrections were made, it was obvious that scientists wanted more. And so the dawn of James Webb started then in the early 90s. The reason we have space telescopes is because of our Earth's atmosphere. Here is a picture taken of Cyprus from a low Earth orbiting spacecraft, and you can see the atmosphere in the background. So all those layers of gas, they absorb and scatter much of the light that's coming from the universe, and we need to be above that layer to make the best observations we possibly can. So pretty soon in space, in our histories of space satellites and space technology, we had space telescopes. So the first one was launched in, I believe, the late 60s, and since then there's been a plethora of actual instruments. So many space agencies have put instruments up, and we've reaped the benefits of their discoveries. James Webb gave us an excellent Christmas present. So last Christmas, 25th of December, there was a successful launch from French Guiana, which is an ESA launch site. James Webb Telescope was a collaboration mainly between NASA, ESA, and the Canadian Space Agency. And so different agencies built different parts, different equipment, and put them all together in the US at a NASA facility. And the payload was delivered to French Guiana, where it was launched by this Ariane 5 rocket, which is a very old rocket and is about to be decommissioned, but it was a very successful launch. Now, in 1996, scientists formally went to the US government at NASA and declared that they wanted this giant infrared telescope put into space, and NASA agreed. And so in 1997, the project started to be funded. And in 2002, teams were selected from all over the world and construction began. A launch site was chosen in 2005 and the mirrors were completed in 2011. Brilliant. So 18 hexagonal mirrors completed, everything due to be put into place and launched. And then there was a 10-year delay. So I know from anxious astronomers that they kept, 2015, when is it going to be launched? 16, 17, 18, 19, 20, 21, and then finally in 2021 it was launched. This is what it looks like in its final form. This is what is actually in space at the moment. So there's a huge mirror, primary mirror, made out of 18 hexagons that had to be folded during launch, because this is so large an area that it cannot be taken up into space with our current technology. There's also a giant sun shield that cools the mirror down. The mirror has to be kept very, very cold because infrared rays are given off by objects with temperature. So if the mirror has a significant temperature, it would give off infrared rays, which would actually affect also with the quality of the image. And in this slide, I have a comparison of the famous Hubble telescope primary mirror compared to the James Webb Space Telescope's primary mirror. So you can see that it's 6.5 times 6.5 meters, whereas the Hubble is like maybe 2 meters in diameter. And you can see that because of that big difference in size, you've got a much more powerful instrument. What the good thing about everything that's being discovered presently to do with NASA, you've got lots of open source documents available, and there are 44 time lapses of the James Webb Telescope being built. So this is one of the ones that I selected. It shows you how the secondary mirror is deployed in the lab and how the light hits the main primary mirror and then is reflected to the secondary and delivered to the instruments. There is a soundtrack here as well. So I'm going to share the sound. Here we go. Oh, started again, right. Anyway, can you hear me now?
Yes.
Okay, excellent. So that is how the secondary mirror on the boom was deployed. And again, a lot of folding was necessary. It was a very intricate operation and excellent engineering to get this working. And there were hardly any glitches. It was clockwork. It worked really well. And Webb is now sitting 1.5 million kilometers away from the Earth. So it's actually sitting at a distance that's significantly further than the moon, as you can see, and many, many times further away than the other space telescopes that, for instance, Hubble. And it's in that special position for a number of reasons. And the main one is that when it sits in this special position, it is effectively orbiting around the sun. So the sun shields can block the sun from the mirror and the instruments. The next thing I'm going to show is an animation showing this special point, which is the Lagrange 2 point between the Earth and the sun, and how that actually aids this telescope to stay cool. So the object that's going around in a small circle, L2, that is the James Webb Space Telescope. Its sun shield is deployed, and as you can see, it's actually orbiting the sun, and it's always, the sun shield is always facing the sun to reflect the rays of the sun back and to actually provide the shield for the primary mirror. Okay, now to maintain this position, you need to fire thrusters regularly. So it is a stable orbit, but there needs to be slight adjustments. And there is enough propellant on this telescope to last 10 years for sure. And now engineers are saying maybe that there is 20 years worth of propellant to keep it in that orbit. So that's good news. It was delivered very accurately by the team to that particular point. And as I've explained, the sun, it has to be in this orbit because that sun shield protects it from the sun's thermal energy. And here you have a difference between the hot side, which is facing the sun, and the cold side, which is away from the sun. So the hot side is 85 degrees Celsius, hotter than Cyprus, much hotter. So we shouldn't complain. And the other side is minus 233 degrees Celsius, which is actually quite close to absolute zero. And that's the kind of temperature you need for this mirror and the detectors to actually be able to detect radiation from the universe in the required frequency. So inside the James Webb Telescope, you have four main pieces of equipment. You have some cameras, the NIRCam and the MIRICam. You have spectrographs, and you have a coronagraphs, which is just basically a way of blocking starlight. Because as you'll see in the pictures, that if you have a bright object, it actually dominates in the picture. So you also have coronagraphs to block starlight. So as you can see in this graphic, James Webb Telescope sees space in a different frequency and wavelength to the Hubble. So it's a good complement to the Hubble. The Hubble isn't obsolete. You know, the Hubble's been going for like many decades, and it's provided very useful information. And the James Webb is going to back up all that work that the Hubble did. Now, this here is the near infrared cam. So it's NIRCam, and it works to see red stars, and it's also detecting light that can pass through dust. So dust is transparent in this frequency. Now, the second camera I'm going to talk to you about is MIRI. Okay, so this is MIRI, and that particular range of wavelengths, it can reveal planets, comets, asteroids, and it can actually look at the dust. So sometimes we need to see through the dust, but sometimes we want to see warmed dust to get a good idea of what's going on in some of the structures that we're observing. So 25th of December, it took some time to get to the Lagrange 2 point. Everything was really successful. And in March, we had our first image, and this is an alignment image. And as you can see, they focused on a star, and we have some very, very specific patterns that have to do with the James Webb Telescope. So the star that they basically took a lot of pictures and aligned them and fine adjusted the mirrors to get a very sharp focus. And even this initial image, you can see some galaxies in the background. So you can see these elongated pieces of light here, which are galaxies. Now, to tell if something's from the James Webb Telescope, the moment you see a bright object, you will see 1, 2, 3, 4, 5, 6 spikes coming from it. And this is a diffraction pattern because the mirror segments are hexagonal. Also, the horizontal line that you can see through the middle is from the booms that hold the secondary mirror. So that's a characteristic that you only get with this telescope. So if you see stars like this, you can place a bet that they will be taken, the pictures are taken by this telescope. Then in April, they fine-tuned it very well and checked all the equipment. So here you have the various cameras and sensors being used and actually being set up and tested. And then mid-May was very exciting because we got our first kind of glimpse as to what was going to be, what was promising. So these are taken in only one specific wavelength, and already you can use these to study and investigate the universe. So in these pictures, you can see nebulae, you can see galaxies, you can look at the shapes. And again, you've got these very bright objects that are usually nearer to us that have got their classic 6 spiked pattern. Okay, so 2 weeks ago, 11th of July, we had a taster of what's to come in the future. And the first image, full color processed image that we received was this one. It's SMAX 0723. And it's a deep field view of a galaxy, a very bright galaxy in the middle of this picture. So I'm gonna try and get a little hand up. I just can't remember how to do it. So maybe mouse. Okay. Can you see my mouse?
Yes.
Yes? Okay. So this was the center of what the Space Telescope was observing. And it's a very massive galaxy that's about 5 billion light years away from us. And what's interesting is that it acted like a gravitational lens to see objects that were much, much further and older. Okay, so it bent light, and you can see these elongated shapes around it. And these are actually galaxies that are extremely old. So many, many billions of light years old, like 12 to 13, that have been gravitationally lensed, and we're able to see them. Now, other telescopes have actually looked back and seen gravitationally lensed galaxies, and we've done studies on them, but there's been nothing like this. The clarity of this, the beauty of this, it was quite breathtaking. It took us, took us all in, like, absolutely amazing. And you can see that there's lots of different colors. Now, our eyes don't detect infrared, so these are color coded. And so it gives us a good visual interpretation of what's going on. And humans, therefore, can find patterns visually as well as crunching numbers and data. It helps look for patterns visually because we're very good at spotting, as humans, spotting visual patterns. Now, some of those galaxies that we saw in that picture come from almost at the beginning of the universe. So from this graphic, by the way, most of the images and graphics I've taken are from our free source from NASA's website. So you can see here that the universe started. There was the Big Bang. it expanded, there was a rapid inflation, there was an afterglow light pattern, and then about 400 million years later, the first stars and therefore galaxies started forming. So the Webb telescope can see back as far as this. So it's pretty amazing. Now, the next slide I'm showing has the image that was released to the media on the 11th of July on the left. And this is the same field taken with the Hubble telescope. And as you can see, there's a lot more objects visible just because of the sheer power of the James Webb telescope, the size of the mirrors and the new technology employed. And also, you can tell that that is Hubble because Hubble has characteristic 4-point diffraction patterns. The other thing that's interesting is that it took many days for Hubble to actually get this image because Hubble goes around the Earth. It can't sit and point at one region of the sky for many, many hours because it's orbiting the Earth. Whereas the James Webb telescope, due to the position that it's in, you can get it to observe a spot in the sky for hours on end. So this image here, it didn't take many hours to actually form, unlike the Hubble image, which took many days to gather enough data for this to form, because you can continuously look at one piece of the sky because of the special orbit that it's in. So here I blew up one of these gravitationally lensed galaxies. And what's amazing is you can actually see structure inside it as well. You can see brighter sections, darker sections. I'm sure people will be spending a lot of time already. They've spent time on it. It's just this image, and there's a lot more research that can go into this. Although some people seem to think that they didn't actually go to space and take stars in the first place. So someone zoomed out and found this bird. Someone else knew what had happened and said that that was their kitchen counter. That one was shared by Elon Musk, I think. He liked that one, found it funny. And also other people saw things that I don't think actually exist. So here is the Death Star. So a lot of jokes were made about this particular one. Now, I'm going to now talk about the next object, which is the Southern Ring Nebula. Now, this is closer to us than obviously these distant galaxies that are billions of years old. And it shows a dying star. So there's a star maybe similar to our sun that's in the last throes of its light. So it's gone through a red giant stage and it's shedding its layers and it's changing to a white dwarf. So all of these rings that you can see around this are actually layers of a dying star being shed into space. And again, it's an object that was well studied by Hubble, but the difference is that with this telescope, you can see through the clouds. So you have two images and they are from the different cameras on board the spacecraft. So you can see one is actually showing you the clouds and the other is showing you through the clouds. And you can see that there are actually two stars in the center of this nebula. So this planetary nebula, which is not actually anything to do with planets, but it's actually a dying star. And you can see that there is a faint star, and that's the star that's dying, with a companion star. So this is obviously a binary system that is still actually, they're still orbiting each other, and that's causing this unique formation to occur. So it's not like a concentric. It's causing waves in the gases, in the dying stars' ejected gases. Now, this is this is the image of the same nebula from Hubble, and you can see that it is also very beautiful, but you can't see as much structure. And what I've done is I'm going to put superpose the image from James Webb Telescope over it. So you can see Hubble is great, but with this new telescope, you can see through the dust, you can see layers, you can see a lot more, what you can understand a lot more about how that may have developed like this, what might be going on. Now, I can see that there's a few people in the UK. In the 90s, there was a very annoying character called Mr. Blobby on TV, and someone tweeted this. And this one actually made me laugh because I found that character very annoying. Oh no, James Webb Space Telescope, what have you done? They brought Mr. Blobby back. So again, the memes this time were absolutely like this one. I just laughed out loud because I didn't like this character. Okay, now next image, the one that I have as my background picture, absolutely stunning. It is the Carina Nebula. It's not the same kinds of nebula as the last one we saw. This one is where stars are being born. So it's clouds of dust. That is a major star forming region. And it looks like there's cliffs and, you know, it's absolutely stunning. That's why I chose it for my background. And you can see that there's this very deep blue area with really bright, newly formed, powerful stars. And it appears that the radiation from these stars is actually pushing the nebula into a shape. So very interesting again. And what is good about this one is that you can actually see through these clouds. So it's a very similar picture as the Pillars of Creation, the famous picture from the Hubble telescope. And you can actually see these new, so there's stars that are being born actually inside the clouds. And then these stars that are at the very energetic stages of their life that have already been born, that are pushing this dust down. It's absolutely amazing. And I keep staring at this one. And you need, you know, it's very, does this radiation cause the stars in the nebula does it limit their growth in some way? So all of these are questions that you can study from a picture like this. And these are only the first images we have. So this is another meme. This was prepared by NASA themselves. They were waiting for this time. So it's the same structure, the Carina Nebula imaged by Hubble, and then imaged by James Webb. So as you can see more details. You can see the stars being formed in that nebula, the birth of stars and maybe new solar systems. Now, the next object that was showcased in the beginning of July, the 12th of July, was this one, Stephan's Quintet. Now, this has been imaged for many years by amateur astronomers, can easily image this one. And this was actually the one that required the most, is the largest area. And it shows a group of 4 galaxies interacting and colliding with each other. So it's like a death of 4 galaxies. And there's another galaxy that is close, but that's actually not part of this, that it's not bound to the other ones. So it looks like it's close to them. That's why it's the quintet, because it's 5 galaxies, but it's not actually bound, it's closer to us. So that one isn't taking part in the collisions, but you've got one here, one here, one here, and one here. And they are basically galaxies merging. And very exciting picture. Again, a lot to study, a lot to see, much more detail. You can see through all that dust. You can see that there is very, very bright spots, suggesting, you know, like a supermassive black hole powerhouse in the middle of these galaxies, and a very exciting image. And again, it was very beautifully imaged by Hubble as well. So you have on the right-hand side here, you have the Hubble image, and on the left-hand side, you have the James Webb image. So you can see that there's different details coming out between one and the other. So you can see that there's, you can see the more of the interactions. Now, the final image that was released on the 12th of June was not really an image, it was a graph. And it's a very exciting graph. So how this graph was formed was by an exoplanet called WASP 96b passing in front of a star. So the exoplanet took about 6.5 hours to transit in front of the star. And while it was doing that, the James Webb Space Telescope analyzed with its spectrometers what was going on, and it discovered that there is water in the atmosphere of that gas giant exoplanet. Okay, so you can't actually, it didn't actually image the planet, but it imaged the atmosphere of that planet, which is really exciting because you can see that there is most likely clouds of water in this gas giant. Now, there are lots of these hot gas giants, exoplanets in other star systems, in planetary systems around other stars. It's quite a common type of planet. They're large, but they're a lot closer to their star than Jupiter is to our star, and that's why they're hot. So I have heard a rumor that it's going to be turned onto the TRAPPIST system, which has more Earth-like planets. So I've heard a rumor that it will be turned to observe something that is more Earth-like shortly. And I can't wait again for that to come out. Okay, so they were the big 4 pictures shared with us at the beginning of July. But then there was this leaked pictures. This leak. And this appeared on Twitter. This is, as you can probably notice, a picture of Jupiter, and it's imaged with a very basic image with the James Webb Telescope. Now, the reason that they imaged Jupiter is because they haven't published or released any images of fast-moving objects so far. So this telescope is designed also to look at things in our own solar system that are moved relatively quickly compared to the many galaxies billions of light years ago, or the exploding, dying, or the planetary nebula, etc. So Jupiter and its moons move fairly quickly. It's a very dynamic planet. Now, this structure on the left is actually Europa. So it's got the spikes, the characteristic spikes. It's actually Europa, and it's been covered by a black dot, and that's that coronagraph I was speaking about at the beginning. So the instrument that, if something is too bright, you can use this instrument to cover it so that you can concentrate on other parts of the imaging process. So that's Europa, and you can see by Jupiter's spot that there's the shadow of Europa on Jupiter as well. And the conclusion of this was that, yes, we can use the James Webb Telescope quite successfully in our solar system. This is another one. It shows Jupiter again, and there's a very faint ring. So it's detected a ring around Jupiter, because Jupiter does have rings around it like Saturn, but it's very difficult to observe. So the James Webb Telescope observed the ring around Jupiter as well. Now, back to the first image I showed. So this is being studied, and a major, probably a probable discovery has been made already. In part of this image, towards the bottom left-hand corner, probably the oldest galaxy ever discovered has been found. It's called Glass Z13. Okay, so it's in a segment of this image with the many, like hundreds of galaxies that you could see there. And with one of the instruments, they can measure the redshift. So it's got a big redshift, which makes it probably the oldest galaxy that we have discovered. So this is very recent. This was published, I think it was published on the 20th of July was the first paper I read about it. And then it's been more in the media in the last couple of days. So it's thought to be 13.5 billion years old, and it's 100 million years older than any other galaxy that we have measured before. So it's really, really exciting. So already we have an actual and probable discovery, and surprisingly, it's very bright and big, and it doesn't make much sense if this is actually the case, if it is actually that old. It's big, you know, it's at the beginning of the period where galaxies were being formed. So it's surprising to find an object that's so big. So I'd like to draw this to a close now with a comment from NASA. This telescope is going to be very, very important in the future. It's worked absolutely brilliantly so far. And that's due to the international collaboration and the planning. And so ESA, the Canadian Space Agency, NASA, all have their parts to play, and they've done an excellent job. And I thank you for listening. If there's any questions, please, now's your chance.
Could I ask you a question?
Yep, sure.
Why is it called the James Webb Telescope?
Okay, right. So there was the, you know, the Apollo program that landed the first humans on the moon.
Yeah.
James Webb was the principal part of that program. So he was like the director of that program. So that's why they named it after him.
Cool,
So
thank you.
good question. So yeah, there was a little bit of controversy about the name, but it stayed James Webb.
So I have a question it's a question from a standard amateur photographer. Does there also exist a possibility to use polarization filters on it?
So there's a bunch of filters on it. I don't know if there's a Polaroid filter, but I assume there should be. So each instrument has filters, and what's really great is the specs of each instrument is open source. So if you go if you do a search on the NASA website, you get the specs of everything, and it's amazing that it's like that. So if you really, I didn't check, but it's possible that there is one on there anyway.
That might be very interesting. Thank you.
You're welcome.
Kate, whilst the telescope is rotating around the Lagrange point 2, does it remain in the shadow of the Earth, or is it relying entirely on its tennis court size?
The heat screen.
Yes, that's right.
We can look at the orbit again. So it probably it's very far away from the Earth. So I guess that is part of the factor that would aid it, but I think it's probably mostly due to the heat screen. Alexander, do you want to add anything to that?
Yes, of course.
Yeah.
At the KITION Planetarium and Observatory, I make with students a task. If someone is precisely in L2 point, how much of the sun is covered? And the answer is 80%, if I remember correctly. So, but the main point here, the James Webb Telescope is not precisely on L2 point. it orbit around it, and it orbit at so far away from the central position that it always sees the sun completely.
Yeah, that's what I thought, because of the sheer distance that it is away from. Like, I think it's 4 times further away from the Earth than the Moon.
Yes, but
yeah.
still no difference. So 1.5 million in comparison with 150 million, it's just 1% farther. So practically completely the sun illuminated the shield of the telescope completely. So there is no shadow of the Earth on it, as far as I see. But I have, if I may ask my question, what's about energy? How energy comes to constantly be on this? From where energy comes to constantly be on this rotation?
Okay, so basically there is a propellant on board, and the propellant is predicted to last at least 10 years, because minor adjustments have to be made to keep it in this orbit, because it's not gonna just stay there. But currently we don't. I mean, it's such a shame that it's got a limited lifespan. Like I said, because the Ariane 5 and the orbital dynamics was so good, it was delivered very well into its slot. So some engineers consider that there may be 20 years of propellant on board it. The other thing, believe it or not, there's a docking ring on there, and there is a slot that you can insert more propellant. So in the future, maybe when our technology and our capabilities increase even more, maybe something could go and service it eventually, which is quite like, yeah. So they've planned this. So they planned it, and so it does have a docking ring, and it's not. The other thing that I didn't mention is the only blip so far has been the micrometeorite impact onto the mirror. So there's been more than expected, more than they modeled, and one of them was quite energetic, so it did a bit of damage. So that's the only blip that that's occurred, is that there's been a little bit more debris out on that spot than they were expecting.
So most probably we would not be need new fuel, just because of the quality of images will be destroyed by micrometeorites. Okay, we will see anyway.
Yeah, we'll see.
So Kate, what do you think will be the next stage? I mean, they're obviously planning ahead, aren't they, for the replacements? I mean, like we have the sort of massive array of individual telescopes, or is it in Nevada or Chile or wherever it is? Is it possible that something like that could eventually be sort of put into space as well?
Well, yeah, I have seen plans where this is in the future, that you can digitally print. I don't know how they're going to do that with the mirrors. So there's plans to digitally print some bits. There are some concepts for really large telescopes in space. So this is there for the gravitational, for the one that took the black hole. Again, they've thought that maybe they could have a baseline on other objects like the moon and other planets. So in the pipeline there are going to be bigger ones. Yeah, in the pipeline there are going to be bigger ones, because we're never going to use something like the James Webb to see an exoplanet like we see Jupiter, for instance. It's just a pixel. So eventually something's going to be built that can do such a thing, image such a thing.
So what's the purpose to observe in infrared? What is the main points to see and which we miss on the Earth?
the main points to see in infrared that we miss on the Earth. Well, we can't see the infrared from the cool objects, the objects that are very, very redshifted. So I think, and also there's a lot of absorption in the infrared wavelengths on Earth.
As I understand, you practically mention all of them. So
Yeah,
the galaxies which are far away,
yeah,
invisible light, they move due to redshift to infrared and are not visible from the Earth anymore. So James Webb Telescope could show it to us.
I mean, there are other infrared telescopes that actually show this as well, but nothing on this scale.
Yes, of course.
You know,
this is
like,
very
this is the
detailed.
thing, you know. The objects that came out of that SMAC image compared to any other telescope is nuts. How many different objects came out that we haven't seen before.
And star formation clouds again,
Yes.
they are called, and that's why
Yeah.
we could not see it from the Earth. For us, it's just black. So a lot of discoveries are coming.
I mean, I'm not entirely sure what the discoveries will be. We'll just have to see. It's very exciting.
Yes, indeed. It already at the very beginning showed it all its capabilities. Maybe not all, but at least main of them.
Yeah.
What infrared light could deliver to us, to our knowledge.
I would like to thank you, Katie, for your excellent presentation. I would also like to thank everyone for joining us tonight. It was a wonderful experience, and it was all the info gathered together, summarized by Katie, because all the information and new data are coming so fast that we cannot catch up with all the info and data, and they are very important. And I believe that Katie, in a very nice and plain way, she presented everything, and we are really, really thankful for that, Katie.
Yeah.
Thank you for having me. Have a nice evening, everyone.
Have a nice evening, everyone. Thank you for joining our online Science Café. We are waiting for you on the last Tuesday of next month, and we're going to announce soon our new topic. We will send you a newsletter again at the end of the other month. So hope to see you again, same time, same place. Keep the link. Once you've logged in with this link, you can follow the same link and you can log in anytime.
Thank you, George.
Thank you, Jonathan, for your cooperation. Say hello to us from us to the waiting astronomers. Thank you, Diana. Thank you, all the newcomers. Hello, Chris. You were here with us last week, and now you're back in our place.
No,
Yeah,
he is next to Sombrero.
Yes, apologize for no kebab tonight and no beer, but
yeah, I didn't get
Hi,
back
Chris.
to.
Hi. How are you? It's a
Thank
coincidence.
you all for joining.
Next time, George. Next time.
Next time.
Thank you. It's good to see you.
So,
Bye.
see you all.
Bye.
Bye for me.
Okay,
Bye, guys.
thank you,
Thanks
George.
for joining our online science career. Bye.
Bye.
Thank you very much.
Night,
Bye.
John.
Bye. Bye.